Everyone thinks a leaky faucet is just a random annoyance. They're wrong. It's a tiny, rhythmic pulse in the quiet of the night. Drip, drip, drip. That persistent, almost hypnotic sound from a leaky faucet. We often just want it to stop, but rarely do we pause to truly look at it. Because within that simple, repetitive action lies a fascinating dance of physics, a subtle science governing why each drop seems to be almost perfectly identical to the last. Think about it. Each drop detaches with remarkable consistency. It's not just a random blob of water breaking free. There's a precise mechanism at play, a delicate balance of forces that dictates the size and timing of every single drip. And understanding it helps us appreciate the hidden order in the most mundane parts of our lives. The primary player in this microscopic drama is something called surface tension. Water molecules, you see, are quite fond of each other. They form strong bonds, especially at the surface, where they're not surrounded by other water molecules on all sides. This creates a kind of elastic skin, a thin film holding the water together. As water accumulates at the end of a leaky faucet, this surface tension is what prevents it from immediately falling. It clings to the faucet's opening, forming a small bulge, a perfect sphere in the making, defying gravity for as long as it can. But gravity, of course, is a persistent force. The water continues to build up, adding weight to the forming drop. Imagine a tiny balloon slowly inflating. The surface tension is the rubber of the balloon, stretching and holding. But eventually, the weight of the water becomes too great for the surface tension to hold it anymore. At a critical point, the neck of the forming drop narrows. This is where the magic and the physics really come into play. The forces of gravity pulling the drop down and surface tension holding it up reach a precise equilibrium, a tipping point. This exact moment, the point of detachment, is not random. It's governed by a principle known as Tate's law, or sometimes the law of equal volumes. It states that the weight of a drop of liquid detaching from a tube is proportional to the surface tension of the liquid and the radius of the tube. For a given liquid, like water, and a given faucet opening, these variables remain constant. The surface tension of water doesn't change significantly in your home, and the size of your faucet's opening is fixed. This consistency is precisely why the drops are so uniform. The drop forms, grows, stretches, and then *snap*, it breaks free. But it doesn't just fall straight down. As it detaches, the remaining water at the faucet's opening snaps back, a phenomenon called capillary recoil. This rebound can actually help pinch off the drop cleanly. What's even more fascinating is that sometimes a tiny secondary droplet, a satellite drop, can form just as the main drop breaks away. This little tag-along is another testament to the complex interplay of forces in this seemingly simple event. The temperature of the water can also play a role, albeit a subtle one. Colder water generally has slightly higher surface tension than warmer water. So, a cold drip might be ever so slightly larger than a warm one, though the difference is often imperceptible to the naked eye. Even the material of the faucet can have a small impact on how the water adheres to it, affecting the initial shape and growth of the drop. A very smooth, non-stick surface might allow drops to form and detach a tiny bit differently than a rougher, older spout. So, the next time you hear that familiar drip, consider the delicate ballet happening right there in your sink. It's a perfect example of nature's elegant engineering, a tiny, repeatable experiment playing out over and over again, silently demonstrating fundamental principles of physics. From the surface tension of the water to the pull of gravity and the precise geometry of the faucet, every element contributes to the perfect uniformity of those drops. It's not just water falling, it's a testament to the order that underpins our world, even in the smallest details. This isn't just about leaky faucets, either. The same principles of drop formation and detachment are crucial in many fields. Think about inkjet printers, where tiny, uniform drops of ink are precisely placed to create images, or in medicine, for controlled drug delivery. Even the way rain falls from clouds or dew forms on a leaf involves these fundamental interactions between liquid, surface tension, and gravity. The universe, it seems, has a preferred way of forming drops, and it's remarkably consistent. It reminds us that there's always more to discover, more layers of understanding, even in the most everyday occurrences. The seemingly simple act of a drip reveals a world of intricate physics, patiently waiting for our curious gaze. So the next time that persistent drip keeps you up, instead of frustration, perhaps you might feel a touch of wonder. A small, uniform moment of physics playing out right there in your home, a tiny rhythm of the universe. Subscribe if you're curious about the hidden science behind the ordinary world around us.